Hi there, this is Dr. Hisham Saeed. So welcome, this is the third part of this lesson on cost management. Big part of it is cost estimating. And in the first part, we'll learn about the different types of cost estimates. And the first one is the rough order of magnitude, ROM cost estimates. So this is what we're gonna learn about in this video. We'll explain the use of empirical cost formulas as one way to develop ROM estimates, and also the use of square foot cost data to develop ROM estimates. So rough order of magnitude estimates are used in the early planning phases and design phases of a project with no or very little information. So an owner can actually use or develop rough order of magnitude estimates if they know what they're doing without the help of an engineer. Cost is calculated as a function. It's generally a very simple function of a single physical variable representing here the project. So it can be a floor area like in buildings, or length in highways, so you can measure it in every mile or every foot of a highway, 6 lanes will cost typically that. And then production volumes for like fabrication plants, or if you think about it like in hospitals, how many beds, or in schools, how many desks. So people can come up with cost rates relative to these features of the project. And these features, I can look at it from two different ways of developing rough order of magnitude. The first one is empirical formula. So it has a function, a formula that can change over different ranges or having a specific trend, or a very basic square foot estimate. So we'll see each one of these approaches to develop rough order of magnitude estimates. So the first one, having an empirical formula, it's a function. It's just a math function as a function of usually just a single variable representing the size of the project. It can be a linear formula starting with a fixed cost. So regardless of the size of the project, you will just always incur a cost like permitting, design, at least, and then you will incur more costs with the size, increased size of the project. You can have a nonlinear formula. This one starts with 0, but you can represent it starting at an intercept value. But this one here is more like a flattening the curve here. The bigger the size is, so that's kind of the economy of the scale. So the more you do, the less cost it will be, or the more efficient you will be in building this facility. Or you can have complexity curves here. The curves of complexity you can build a huge power plant, but it will cost you infinite, budget to build it. So complexity here comes with a cost that is exponentially growing. So these formulas here are developed using historical data from previous projects that you did before, or you have access to the data. So this is what Whit Holz, it's a researcher, he's a researcher, or she, I'm not sure the last name here, but Whit Holz and partner authors did a study and collected a lot of the data of a lot of desalination projects and come up with this formula. It's basically a function of one single variable here, which is the capacity of the plant. And of course, it's not a linear function, it's a logarithmic function, but it's plotted here using a logarithmic scale, so don't be confused with that. And they consider here, this is from a study that kind of compared Whit Holz data and model to other models. So these USBR is another model. This is a U.S. Bureau of Reclamation, I guess, or I'm not sure what this stands. It's a public agency that also have managed to figure out a formula from its own data. So you can see they're pretty close, and it's very simple to use. The other approach to rough order of magnitude is square foot estimate. So publishers and research firms kind of commercialize available data by analyzing it and categorizing it and really doing a good job in publishing it in an organized way. And they follow, the organization here is done by looking at standard models of buildings and developing a kind of a square foot cost model for that specific model of building by tweaking some variables here and there to change the square foot cost estimate or cost rate depending on some specific conditions. So we're using here RS means, and kind of I try to simplify it in just one formula following the empirical approach method. But the total cost in a project would equal to the floor square foot cost, FSFC, and that's you bring it from RS means. So you will see how you get this from RS means, and that times you multiply that by the floor area. So it's the sum of the gross area. So it's just the footprint of the whole building. You multiply it by the number of floors. So that's the floor area. It's the collective floor areas over different floors of the building. And then that's the above ground. Below ground, you do the similar approach, but now dealing with the basement area and the basement square foot cost. And then you add any additives to reflect things that were not considered in the building model that was used to create the square foot cost rates. So you can include special features or finishes or equipment. So for RS means it has 77 model buildings. You can see this is just a sample of them. And for every one, they have 2 pages. So the left page is showing you the cost, square foot cost data for different configurations of it. And the right one is showing you a model of such calculation for this model, but for a specific case, like we'll see very soon. So the left page here is matching with the formula. So the floor square foot cost, this value from this table here, the basement square foot cost, just one line here, and there are multiple additives you can include in the estimate. So the numbers here do not reflect additives or the things that are listed here, like appliances in this case, or elevators. And then this shaded number here, if you can see it, for this one, it says that the square foot cost is $183.4 per square foot. That's calculated based on this sheet of calculations. This is just given as an example. It's just an example of one case within that model M20, which is apartment 4 to 7 stories. So this model here is a little specific. It says it's a 6-story building with this story height, this square foot area. And you can see the different features, and we'll see that in the next slides. But if we focus on the left page here, so in the left page here, the way to use it is you look at the square foot floor area of your building, again the total one, the gross area of the whole building, and you try to see where are you in these multiple options given to you. Hopefully you are within. So if you're not like exactly the same value, you can do approximation or interpolation between the values. These linear foot perimeter values are the ones that make sense with this area. So like if you have a weird shape with a lot of corners building like that, you will have a different perimeter than this, and this should be increasing your cost. So we'll see how to adjust for perimeter. But typically a 60,000 square foot area building will have around 500 linear foot perimeter. Next, you look for what type of facade you have, so the exterior wall, and what type of framing you have or structural system. So together you start to match again, and you see there are limited options. So you have to deal with what you have, or what you get from the square foot data. So maybe in one case you will have not a rigid structure or reinforced concrete. Maybe you will have a masonry structure, so you will not be able to use that model anymore. But try to match the exterior wall with the structural system. Once you know a column and you know a row, you can pull the square foot data. This is the basement square foot cost that also goes into the formula. And this is the row where you can make adjustments. So let's say your perimeter, your square foot is 60,000. Your perimeter is not 500. It's like 700. It's kind of weird shape of a building. So these 200 extra perimeter linear foot, for you multiply 6.9 times 2, because this 6.9 for every 100 linear foot extra than the standard one. So you adjust your calculations this way. And also another thing to adjust for is the story height. So the height of the story in this model, in the second page of this model, will tell you maybe it's 10 foot and 6 inch. If your height is different, then you will need to adjust it for every foot difference. This is the cost to add up to the square foot numbers that you have here. We'll see an example of that. Now the detailed calculations, or the example calculations here, you have to pay attention to the description because it tells you here the story height. Another thing, you can also see here that they are including here the fees for architects and engineers and the contractors. And you can see now the detailed, not detailed, but what calculations they did to come up with this square foot cost, 183.4. You can see most of it came from interiors, 27%, partitions, finishes, and all of that. The next biggest item was exterior enclosure. So we can go over that as a list of what's really included in the scope of this $183.4 per square foot. And you can see what assumptions they made, and if it is completely different than yours, then probably, if you know that it's completely different than yours, this means that you haven't design information. Then they should not do square foot estimates. You should do more detailed one, like we'll see in assembly-based estimates or work-based estimate. So, but generally we'll accept the model because you don't have information about your design. So, but it's good to know what you're actually dealing with. Also one thing is just run calculations and check it. So here, this is standard foundation. It's measured by square foot ground. So it's only the footprint. You're not multiplying by the floors. So it's 8.4 per square foot of ground of where the foundation will be. But you're trying to get the square foot per floor area. So for all the buildings here, the total. So what happens here is you divide that over 6, because the building here is 6 stories. So that's the number that adds up to the large number of square foot cost that we have at the end. Another thing is how many exterior doors are assumed here. If each door costs like that, and you end up with a 55 cents per square foot. So how they came up with that? I will reverse engineer it to see that if I multiply 55 cents per square foot times the area I have divided by the cost of every door, I will end up with 6 exterior doors. So this building will have 6 exterior doors. So it's good to run these calculations to make sure or make sense of the model. I don't say they made a mistake, but for your own sake to know what's really included in this model. This is a quick example we'll go through. So you're working in an engineering firm and you're trying to come up with an estimate for this building. You see a whole building is represented by just a paragraph because you don't have the design yet. So the building is a rectangular shape. It has this dimension and the north and south, and the east and west sides I have that shorter dimension or length. The building has 1-story basement, so you have to adjust for basements here or include basement with a total area of that. The building will be built using steel framing. The story height is 11 feet 4 inch. All exterior walls are brick veneer. So the facade here is this type, except for north side. So the north side is one of the long sides here, will be covered by curtain walls. So probably it's the face of the building, like on the street, and the other sides are just the side not facing the street. It's not the front face of the building. So the front face of the building is covered by curtain walls. Calculate the rough order of magnitude for this design. So if you don't like it, maybe you can change the design for the owner. So the first thing I will calculate is the footprint area. So it turns out to be 11,460. I have 7 floors, so I get up the floor area, the total floor area of the building, and the perimeter here is 502. Now I look at my table, I see here that's around 80,000, so I will stick to this column. And I see here the perimeter is 530, and mine is 502, so it's also pretty close. It's not that bad. Especially that for perimeter, I have to have 100 linear foot difference to adjust for it, so I'm fine. Next is now which system. I'm dealing with rigid steel, right? The framing, but I have 2 different types of facade. Most of it is brick veneer, but some of it is curtain wall. So I need now to figure out, should I use this number or this number? So you will do interpolation by considering how big of my facade is actually curtain walls, and it's 38%, considering the ratio between that side of the building covered by curtain walls versus the other side, or the whole perimeter. And then you do interpolation here, 38% considering that this is the curtain wall building and 62% of that. So I end up with a revised interpolated square foot cost of so far. Next thing is the adjust for height, because I see here this is a 10-foot 4-inch model, but my building is 11-foot 4-inch. So it's 1 foot difference. If I look here, adjust for the height, for every 1 foot difference, I add $2.4 per square foot. Makes sense, because this height will result in bigger columns, more facade, so a lot of cost impacts. So you will add up these two here, you'll end up with now a revised or adjusted square foot cost of $173.66 per square foot. What other things I can do is I can look at, I have a basement, so the square foot cost is that, and the area of it is given 4,200 square foot. Multiply that by the basement square foot cost, and figuring out the floor above ground square foot cost here, I ended up with this building will cost around 14,100,000. And that's it. You bring this number to the owner. If it's within the budget, you will move ahead with detailing the design. If not, then you will think about maybe sacrificing the curtain walls and give the owner a building that's fully covered with brick veneer, or maybe cut a floor. So cut out the floor. So that's kind of the early decisions are made by these rough order of magnitude estimates. Now, if you like the design and the owner kind of like the budget, you move on, you detail the design. Now, these estimates are not, rough order of magnitude estimates are not sufficient enough, because are not reliable enough, because now you should have design information to build a more reliable estimate, a more accurate estimate. So we'll see that in the next parts when we cover assembly-based estimates and work-based estimates. So in this part here, we covered rough order of magnitude estimates, which can be done by empirical formulas or square foot estimates. Thank you. I'll see you in other videos.